In this section, I'm going to look at how you can get features from text that you can use inside discriminative models for various kinds of classification tasks. So in these slides and in most Maxent work, by a feature, what we're meaning is an elementary piece of evidence that links between what we observe, which is the data piece D, and a category C that we want to present. So a feature is a function with a bounded real value. So what we can do is write that we have a feature f, which is mapping from the space of classes and pieces of data onto a real number. So here then are a couple of examples of the kind of features that we have. So let's look at these features with respect to some particular pieces of data. Okay, so the first feature, the purple feature, is saying that the class's location, so in these example pieces of data, I'm assuming that I'm looking at the last word in the sequence, and then the class above it is being shown in orange. So the feature picks out examples where the class is location, so that's the two pieces of data on the left, and the previous word is in, and the word is capitalized. So all three of those criteria are true of these two pieces of data, but aren't true of the two pieces of data on the right, really for multiple reasons, both because the class is wrong and the preceding word is also wrong. Okay, so then if we go on and look at the second feature, it's again saying the class's location, and for the rest of the feature we can put in just anything that seems like it'll be useful. So we might think it's a useful feature to know whether a word has in it something like accented Latin characters, so it's not just plain A to Z, but has some other characters in there. So here, you know, we've sort of noticed that some names have things like accented letters in them. So this feature then will be true of this piece of data. And again, it's not true of any of the other pieces of data. Okay, so then let's look at feature 3. So feature 3 says the class is drug and the word ends in C. So that's a feature that's true of this piece of data, but not any of the others. So in general, that's what's happening. We're imagining for our training, we'll have data which already gives us the right answers. There'll be some words and that they will have a class. And so in this example, we're then also assuming that we have a particular position that we're looking at, so that this is the basic word W. And then when we want to, we can refer to something like the word -1 here to ask features about other nearby words. And so then our feature will then ask some question about the class, is it a drug, and some question about the words, where normally it won't sort of just ask for the complete sequence of words, but might ask for features of them, like an individual word or something in between, like in this example we gave where we're just looking at whether the word ends in the letter C. At that point, the next thing is that the model will assign to each feature a weight, where the weight is a real number, so it might be something like 0.3 or -0.2. So this isn't the value of the feature, this is the weight of the feature. And so a positive weight votes that this configuration is likely correct. It's the kind of thing that happens in real text. So that's something like, for feature 1, well, if the preceding word is in and the word is capitalized, well, that's indeed a good indicator that the word is a location. So for feature 1 that matches these two pieces of data, we'd expect it to have a positive weight. Then the other choice is you can have a negative weight. So that a negative weight votes that a configuration is likely incorrect. So we could have another feature, for example, which was kind of like feature 1, but might be feature 14, which said the class equals drug, and the rest of the condition was the same. And so that feature would match a different classification where we had in Arcadia, and we were saying Arcadia was a drug, and feature 14 would match that configuration, but what we'd like to say is that that's unlikely to be correct, and we could express that by giving a negative weight like -0.6 to it. Later on, when we're working with features, we're going to crucially make use of two expectations. So an expectation is an actual or predicted count of a feature firing. And we have two expectations. One is from our supervised data, we can just actually look how often a particular feature is satisfied by pieces of data. And so we'll refer to that as the empirical count or the empirical expectation of the feature. So that's this guy. We simply just look through every piece of data that we're training off and we ask, is the feature true of that piece of data? And we count the number of times it's true, and that's our empirical expectation. The other expectation is the model expectation of the feature. We'll look at this more in a minute, but what we're going to have is a probability distribution over pairs of a class and a data set. And so what we're going to do is, using that distribution, we're going to consider all classes and pieces of data and then say, well, given that, what is the expected value of f based on the probabilities of different configurations and what the value of f is for those configurations. In the particular case of natural language processing applications, what we find is that usually a feature is of a very particular form. So the feature consists of, firstly, an indicator function, a yes-no Boolean matching function of properties of the input, and secondly, it specifies a particular class. So the arbitrary feature is just a feature of a class data pair, and it's returning some real number. But in practice, the features that we define have this very particular form. So we have a matching predicate against the data, so that's something like ends in the letter C and is a capitalized word, and that's conjoined together with saying a particular class is matched. And the return value of the feature can in general be a real number, but our features here are logical Boolean predicates, and so their return value is either 0 or 1. Now, every feature that we're going to present in this class is of exactly this form, and that's true of 99% of how these features have been used in natural language processing work. And so we can equally say that phi d is a feature of the data D when for each class Cj, the conjunction phi d and C equals Cj is a feature of a class data pair. And so that's our Fi feature pair. So a lot of the time what we'll find is that we'll think in terms of these phi d features, but you should remember that the actual math and programming we write is going to be working in terms of these Fi features, where this I index is being particular to both matching a data predicate and some particular class. But nevertheless, a good way to think about things is that each feature identifies a subset of the data and suggests a label for it. And that's what we saw in the examples before. In feature-based models, the decision about a data point is based entirely on the features that are active at that point. So let's look at a couple of examples of NLP applications and the kind of features that get defined for them. One of the simplest cases is text categorization. So we have an article which has data like stocks hit a yearly low, and it's assigned some topical class here, business. And so typically in these kind of text categorization applications, the features are just the words that occur in the article. So each word type that occurs in the article will be a feature of a phi feature. And so then a complete F feature will be that the word stocks occurred and the class is business, or the word stocks occurred and the class is sports. Word sense disambiguation is the task of determining the senses of words in context. So for example, whether usage of the word bank is referring to the bank of a river or to the financial institution. In making a classifier that decides senses of words, in practice it comes out kind of like a text categorization example where we regard the context of the word as this little mini document around the word. So here we have the observed data, the sequence of words. Here's the word we want to disambiguate, and here it has the particular class in the training data. This is an instance of the money one. So we could just use the same kind of features as here, a bag of words set of features of the words around in the context. But we can also use more particular features that look at particular things in the context. So we could have a feature that says the word before is restructure, the word afterwards is debt. And we could have other kinds of features if we wanted to too. Like we could have a feature that the length of the sentence is 12. You should really think that you can make features in any way you want that'll be good in predicting what the class is. And commonly in practice what you'll find is word sense disambiguation systems have both bag of words features like this, and they have features that ask about particular words that are adjacent on the left and right, and it's been shown that actually having both of those types is useful. Here's one more example that's slightly different, which is when we're working out the part of speech of a word in context, whether it's a noun or a verb. And so here's fall, which can be a verb to fall down, or a noun, and in this particular case its actual class is noun. So if we're wanting to do part of speech tagging, we're likely to want to know particular things about a very narrow context and things in particular positions. So we'd want to know what word it is that we're tagging. The current word is fall. It's likely to be a good indicator of whether it's a verb or a noun, what the previous word is. And this example points in the direction of when we want to do a sequence of classifying decisions where we actually want to classify each word. And that's a topic that we'll return to later when we show how to build sequence models. But the easiest way to think about it is that we're just going to give each word a part of speech in turn. So once we're deciding this word's part of speech, we can assume that we've already given parts of speech to the words that precede it. So we can also use as a feature for deciding this word's part of speech what the part of speech of the previous word was. And so this is this feature here that's saying the previous tag is adjective. So looking at a couple of examples in more detail, let's just go through a couple of bits of work on feature-based classifiers. So Zhang and Ols was one well-known piece of work for doing text categorization. And so the features that they used are precisely bag of words features. So the features are precisely presence of a word in the document and the document class. They actually don't use every word that occurs in the document, and so a common refinement is to do a process of feature selection where you pick out a particular subset of words that are deemed to be reliable indicators. You might be dropping very rare words or also dropping extremely common words that are viewed to be semantically empty. The test set that they use is a well-known text categorization dataset, the Reuters Newswire dataset. And here are just some indicative results of what they find. So they build a naive Bayes model which gets 77% F1 across the different classes. And then they compare several discriminative classifiers. They build a linear regression model. Now, despite the fact that linear regression models shouldn't be right for doing these kind of categorical text prediction tasks because of various reasons, such as the numbers going out of bounds and not being probabilities. Actually, what you can see is that the linear regression works already much better than the naive Bayes model. In fact, what they find is it works almost as well as the logistic regression model. The logistic regression model is a fraction better, but actually not very much. They also train a support vector machine model, which is another very common and popular discriminative classifier used widely for text-based models like text categorization. Its performance is almost indistinguishably different from the logistic regression model. And so that's something of interesting that comes out in a lot of recent work. So you can see that the big difference here is between the naive Bayes model and all of the discriminative models. All the discriminative models do much better, and in turn the differences between the discriminative models are very small. And so a lot of the time, yes, you want to use an appropriate model, but it doesn't actually matter very much which model you choose. What's going to matter very much more is the quality of the features that you define. Another thing that the paper emphasizes that we'll come back to is the importance of regularization or smoothing for successful use of discriminative models. That was something that wasn't used in much of the very early NLP and IR work on discriminative models, but turns out to be very important. There are many places where you can use a Maxent classifier. It's whenever you have some data points that you want to assign to one of a number of classes. So let's just look through a few more examples. So here's a fairly straightforward one, which is where what you want to do is decide whether a period is the end of sentence or an abbreviation. So you might have something like, i.e. you choose, and we have this period here, and what we'd like to say is that this period isn't the end of sentence, and we can kind of think that there are some ways that we could tell that by seeing this abbreviation beforehand. And so we'll be wanting to make features that look at the stuff to the left of the period, and perhaps also things to the right of the period, such as that this word isn't capitalized. We've already talked a bit about sentiment analysis as to whether someone is giving a positive or negative review, and we can make a discriminative classifier for that by putting in features for the words and perhaps other kinds of features like word pair features, different parts of speech, and things like that. Prepositional phrase attachment is the task of working out whether a prepositional phrase like with a beard is modifying a particular noun or verb, and that's getting us into the realm of syntactic decisions. Or more in general, one way in general to make parsing decisions for the structure of the sentence is to build classifiers for the particular decisions that are involved in making the classifier. Okay, I hope that's given you a good sense of what the features are that are used in modern discriminative NLP systems, and some idea of the kind of applications to which they've been applied.